Yeah, I'll try to record.
Oh, I think it's recording, yes. Okay, so, okay, yes. Where was I? Okay, so at the arcade point, as I said, we're able to use, we can relate it to classical computation on these quantum dimer models, and there's a lot of techniques of how to calculate such correlations on classical dimer models. And with them, people have been able to explicitly calculate, let's say, on the square lattice, you have, if you look at the dimer-dimer correlation function, it drops off as a power law on the square lattice, and on a triangular lattice, it drops off exponentially and quite
this
fast.
Is just for this, you're calculating these dimer correlations just in the RK point. Ah, yeah, right.
Okay. Yeah, just at the RK point, yes, yes. These calculations are exact at the RK point. Away from the RK point, from what I found, I only found numerical investigations. Yeah, so
it's not numerical. The 1 over r squared is not numerical.
The 1 over r squared is not numerical.
No, but it's at the RK point.
At the RK point, yes. At the RK point where t equals v, and we know the quantum correlation functions, we can use the classical dimer model on which calculations have been done. Specifically, the classical dimer model has been solved at 63 by Fisher. So it's a pretty old result.
But what? It's a soluble model, or what is it?
It's a soluble model, yes.
Is it? You mean it's based on some combinatorial counting?
Yes, yes. I plan on expanding a little bit on this counting, but for now, I just state the results. I won't do the full calculation of either of these, but I'll kind of say what the general technique is. It's called the Pfaffian technique or Pfaffian method. Okay, so other than at the RK point, I also mentioned that the RK Hamiltonian has several other phases, so which were studied either numerically or studied mainly numerically. So for example, we had these plaquette states, which are kind of pictorially shown here. This is not a valid dimer configuration, as I said, but it's more of a mean field picture of where we expect to find the dimers, depict the probability of finding a dimer somewhere. And we can also, on different lattices, we have different clusters of these dimers. These are all called plaquette states. I also kind of discussed briefly the phase map, sorry, of the RK Hamiltonian. So for a bipartite lattice, this is believed to be the generic form of it. We have the RK point here. We have the staggered phase here, where there are no flippable plaquettes. Here we have the columnar phase, where all plaquettes are flippable. Here it's the plaquette phase I just now mentioned. And here in the question mark, we might have some crossover from columnar to plaquette. That's, I think, what is believed for the square lattice. We might have more complicated plaquette states which involve more larger clusters. So there are several candidates. For the non-bipartite, there is another phase that I claimed occurs, that the RK point is a part of. which is called the Z2 RVB liquid, resonance valence bond liquid. You can think of the Z2 as coming from the Z2 topological invariant. And there's also plaquette states in this question mark here. Another point I want to say that last time I didn't have an answer. Daniel asked me. I said that this phase transition seems to be first order, and that can be kind of guessed from looking at the symmetries of the two phases across the archive point. So they break different symmetries. Here we have rotation symmetry. Here we don't have rotation symmetry. Here we can move like so, like in the x direction once, in the y direction once, and this is a symmetry here. It's not a symmetry. So we break different symmetries. So from Landau theory, we expect this to be a first order phase transition. But actually, people have looked more carefully at the RK point for the square lattice, and they find that it's what's known as a deconfined critical point, and we can actually add some perturbations near this point, and somehow a transition from the plaquette to the staggered phase smoothly. So there is no discontinuity in the let's say the free energy. So just a small note here. Okay, so now we can continue where we left off last time. So I want to talk about another way to look at the dimer models. So this other way is through what's known as the transition graphs. So if we fix some dimer configuration, choose the topological sector, we choose some dimer configuration in that topological sector, and we now look at a different dimer configuration, and we kind of overlap them on top of each other. We'll get a picture that looks like this. It will have loops of here it's alternating colors of dimers or of bonds, that one from the dimer configuration and one from the reference dimer configuration, and also double bonds will have. So we can now consider this picture of the transition graph from these two dimer configurations as representing this dimer configuration. So if we started with, let's say, this resonance valence bond state, with here the first one as the reference dimer state, then instead of these pictures, we'll have these pictures. Just kind of a different way of writing stuff down. And now instead of superpositions of dimers, we have superpositions of loops. So this, for those of you who know it, it smells similar to the toric code ground state, in which it can also be represented as an equal superpositions of all loops. Here, it's a little bit more subtle because not all loops are permissible. Only loops that cross through the reference dimer configurations are valid loops. So it's not, yeah, I didn't write it down. So it's not quite it's only an analogy to the toric code, and not it's not exact, but it gives some intuition, and I'll come back to that very soon.
How do you again construct those loops? You construct with respect to the reference configuration.
So if what I said is just kind of put the two dimer configurations on top of each other, and you'll get this picture. And you'll see you'll have loops and double bonds. That's the only thing you'll get.
Is guaranteed it will be closed?
Yes, it's guaranteed it will be closed because each site is connected to two dimers, one on each dimer configuration.
Yeah, thank you.
Okay, if your graph has a non-trivial topology, you might have non-contractible loops. Here in this picture, all the loops are contractible, but still it's a closed loop. Okay, so we had this kind of transition graph and transition loops representation, and now I want to
get in the RK point. You think about the RK?
No, it's quite general. I mean, this representation of a dimer state using transition loop is exact.
No, that's fine. But I mean, if it's an equal superposition of all loops, then it's the RK point, I guess, right?
Yes. If it's not in, yeah, right. If it's not an equal, yes.
I thought the assumption was that the dimers are orthogonal. These transition loops are the non-orthogonality of the different dimers, right? They have overlaps. Different dimers have overlap because of the loops.
So you're ahead of me in one slide.
So are they orthogonal or not, the dimer configuration?
So I consider them to be orthogonal. I'll answer your question in exactly in the next slide, actually.
Oh, okay.
It's a very good question, an excellent question. And Nathaniel, as you said, only at the RK point will the RVB state corresponding in the ground state of the RK model will be an equal superposition of all permissible transition loops. For other points, different T and V values, it will be non-equal weight superposition of loops. But still, you can use loops to kind of think about them, about these states.
Can you give an example of non-allowed loop which is not allowed?
So let me think. On a square lattice, I think I can't do that on a square lattice. Okay, let's look at the following. I think this works. Let's look at the following.
With the one I drawn would work, right?
Yes, exactly, yes. Here you see that this loop goes has this two-cell loop. It goes through this bond and this bond, and neither of them are in the reference dimer configuration, right?
Yeah.
So it can't be a valid loop.
But it also goes through the top and bottom ones.
Hmm?
But it also goes through the blue bonds.
Yes, but the loop should have alternating. It should alternate between bonds of the
It has to
bonds
be
of the dimer configuration and the reference dimer configuration. Yes.
Okay.
So it's a pretty harsh restriction on the loop. Okay, so next, Asa, this is regarding your question about the orthogonality. If we don't treat the dimer configuration as a orthogonal states, then we do want to think of each dimer as a spin singlet formed by, let's say, two spin halves at the sides. Then it can be shown. I won't show it, that the overlap of two such dimer configurations will be 2 to the power of the number of transition loops. So for example, here there are 2 transition loops, times x to the power of the sum of the lengths of the loops. Okay, and the x is 1 over square root of 2. This overlap is of course always smaller than is at most 1, and the larger the loops, the smaller the overlap, right? Because the power here is of the x is larger. So in this sense, the orthogonality of the dimers that I just kind of started in the beginning as declared them to be orthogonal can be thought of as like some sort of expansion, first order term in an expansion in small x. Okay, so x is the small parameter. I mean, it's a constant number. It's not really a small parameter, but it can be viewed in such a way. And if the state we're considering is a superposition with large loops, then the overlap. People claim that this approximation is valid.
So when you say 2 to the number of loops is when you compare D and D prime and you look at.
Yes, I have 2 dimer configurations.
You're looking at the overlap between D and D primes. There are 2 dimer configurations.
Mm-hmm.
And you say it's 2 to the power of number of loops.
Yes, times x to the power of the sum of the lengths of them.
But loops in what?
So this is again in the transition graph. For example, here, if I compare these two dimer configurations, we have 2 loops. So it's 2 to the power of 2 times x to the power of here it's 4 plus 6.
Plus 2 for the.
I think you also need to count the 2 from the.
Yeah, you need to count it,
table.
otherwise the same state would have 0 overlap. I mean, the state would have 0 norm. If D and D prime are the same, then you only get those double lines.
The factor x is only loops larger than 2. That's the point.
No, it should be the same state. You need to get x to the power 2 times number of loops, right? So it will be 1.
Oh, but loops of size 2 are okay, but anything larger should be suppressed by factor x.
I think it's fine.
So,
I mean, as long as you count the same thing in the power of 2 and in the power of x, then it's fine.
In this formula, I only count in the number of loops and length of loops. I only count. I think you can also count the double bonds. Right?
No, that's in the normalization. You want it to be normalized states, right? So the normalization is the number of dimers, and x is the overlaps of non-orthogonal dimers. So all the dimers would fall off in the normalization, and the loops larger than 2, like 4 or 6, give you factors of x. So that's why if you take x to 0, it should go to 0, unless the number of loops is 0.
No, I think what I'm trying to answer is a different thing. Is how this formula treats this double bond. So you can think of a double bond as just a small loop. So it gives you a factor 2, and it has a length 2 because it's 1, 2. So it's.
No, there's a different combinatorial factors for dimers and everything larger than dimers, because everything larger than dimers appears twice because you have the red and the blue degeneracy, but in the dimer appear only once. So there's a difference in the factors. So that's why you could use the loops larger than 2 as a measure of the non-orthogonality.
Yes.
That's the thesis of my first graduate student at Techno, my first PhD. His thesis was calculating essentially these overlaps of valence bond states. And Moshe Chavilio
אפסד, יודע שפגשתי אותו בהפגנה בירושלים.
נו, איך לא?
הוא בא אליי, בא להגיד לי שלום, זה היה אותי.
זה התזה שלו, עכשיו אתה יודע. אוקיי.
Yeah.
Anyways,
So
counting the loops is counting non-orthogonality. Yeah.
Yes, that was the whole point of this. Just
Right.
to give some more substance to the relation of the dimer models and spin models.
Right.
So again, I just want to summarize. So 2 to the number of loops, which are actually loops, not dimers.
Yes.
Right.
Times x is the sum of lengths of loops.
Again, the actual loops, not double bonds, not the double bind.
So if x is equal to 0, then every time I have even one loop and the overlap is 0.
Yes, but x is not 0. That's
No, I understand it's not 0.
Yeah.
And then if it's the same state, then the number of loops is 0. So the overlap is
these
1.
will both be 0. I think
No. So the
you
overlap
were
is
cut
1.
off. I didn't hear you.
Yeah. So if there is no, if it's d equal d prime, then there are no loops, and then the overlap is 1.
Yes. Yes.
Okay.
Wait, so this is the overlap only between d is the base state and d prime is the state which is the loops
It
are
can be-
relative to the base state. D.
It can be any two dimer states. But in the transition graph, yes, D is the, let's say, reference, and D prime is another dimer configuration. So yes.
Okay.
Okay, so now I want to take a short detour in the classical dimer model and tell you how people calculate correlation functions. It will be helpful also in the some notions from here will also be helpful in the Majorana dimer model. So let's say we have the classical partition function. So this is just a sum of all dimer configuration. Here I give some weights to what's going on here. How do I cancel? Okay. So here I just give each edge some fugacity. So just kind of think of it of e to the minus beta e for some dimer energy or something like that. So just sum of all dimer configurations and the weights of each dimer in that specific configuration.
What is considered an edge again? What do you call an edge?
An edge of the graph is just the two sides that might be connected by a dimer. And here it's a product of all the edges occupied by dimers. Okay, so for example, in this is not an edge. This is an edge that's not occupied by a dimer, and this is an edge that's occupied by a dimer. I'll cancel. Okay, good. Okay, so actually, it's a pretty old result that this sum can be written down as a Pfaffian of some matrix. So just a reminder for people who don't know or remember, Pfaffian is given by this formula. It looks very similar to the determinant. It's actually the square root of the determinant of A. And here, I have here a slight mistake. This should be ZE, let's say IJ. So the matrix should just goes over all. You can think of the indices of the matrix as being the different sites, and it has non-zero value if the edge connected by INJ can be occupied by a dimer, and in this product it will go over all possible pairings of edges, and the only problematic thing here is that you have this sign of some permutation of these, which might give you plus minus signs relative to the actual classical partition function. So an assignment of the plus minus signs in this matrix that gives you all positive, it's called the Pfaffian orientation, or sometimes Castellane orientation for the person who noted this relation. And in his work, he think of this assignment of plus or minus sign as an orientation of the edge that connects, let's say, I and J. So if we have a plus sign here, then the edge between I and J is actually an arrow that points from I to J. And I forgot to say, A is anti-symmetric, so JI should have like the opposite direction, which is consistent with this orientation choice.
Why isn't this, instead of using this Pfaffian, you can use the permanent of this A?
Well, you can use the permanent, but doing it with the Pfaffian
It's more confusing.
I think it has several. It's more confusing, but I think it has some advantage. I think it's easier, computationally easier to calculate the Pfaffian. There are checked stuff.
Continue. We're just chatting.
Okay. Okay. Sorry. Okay. So Castellane in his paper also shows that, okay, so we need to have this we need to find this kind of assignment of plus minus sign or equivalently directionality orientation of the edges. And what he shows that the condition that this orientation should hold, it should have what's known as clockwise odd rule. So if we go along some transition loop, a loop admissible by the transition graph, then then the number, and we kind of go along the edge, let's say this loop, kind of draw, let's say this, then the number of time, and let's say we go clockwise, then the odd term here relates to how many times we go against the clockwise direction. So here it's with the clockwise, with the clockwise, with the clockwise. So we have one here, and one here. So overall 3, and this is odd. So this specific loop I drew has this clockwise odd rule.
Barak.
Yes.
So all the lines along the x direction point in the same direction. But along the y direction they are staggered.
Yes, that is correct.
Okay.
So when we look for an orientation,
This is a gauge choice of pi flux per plaquette, right? That's essentially what you're saying.
I think it can be viewed like this. Yes. So I'll say it like this: the Castellane orientation, what Castellane shows that it needs to obey this clockwise odd rule. And people have shown that for the square and also the triangular lattice, such an orientation necessarily break the translation invariance to somewhat larger cell sizes. So here we indeed we get a doubling of the basic cell of the lattice. And also here you can see that let's say from this side we have an outgoing arrow, and then here we have an ingoing arrow. So we also break this translation symmetry here as well. So that's a good point.
But what is again the rule? Can you state again the rule?
So the rule is summarizing this clockwise odd rule. If you go along a transition graph and you count the number of arrows that goes against your direction, you should find an odd number of such arrows.
Okay.
Okay, and it actually doesn't matter if you go clockwise or counterclockwise.
Okay.
Because these loops are necessarily even. Okay, so such an orientation always exists for a planar graph. Planar graph is a graph that you can put on the plane, and all its edges, the edges don't cross. For more complicated graphs, it might not exist. There have been some extensions to, let's say, torus or surfaces of higher genuses. I don't plan to say much more about that. Okay, so that's just a construct that comes out of trying to solve the classical dimer model, this Castellian orientation and the clockwise odd rule. We'll meet it again soon in the Majorana dimer model in a totally different idea. And again, such orientations always exist for planar graphs. Okay, I can skip this. So this Pfaffian method, I'll just say this Pfaffian method can also is also what gives you the original way of calculating correlation functions. Okay, so another idea that kind of shows really neatly in these models is what's known as fractionalization, where you get a degree of freedom that breaks down to a bunch of others. So to see this, let's now consider something that I say that I forbade before. Let's consider monomers. So here, for example, we had some dimer broken up into two monomers, and we can think of them as we can fix them and then look at how all the dimers in the background move about. We can also give them some dynamics. Let's supplement the RK Hamiltonian with this kinetic term. Now a bond can jump like so, or we can give them some penalty of having dimers, and now they can move about. Now they have dynamics. And they can be thought of as quasi-particles, and we can think of how they behave. These new quasi-particles behave in different phases. Also, these dimers they correspond in the transition loop to open loops. Another way to think about them is if we go back to our spin picture of the dimer configuration, then they can be thought of as holes or spin halves. So for, let's say, here in the dimer, we break this spin singlet into two spins half. So each black one can be thought of as a spin half that's kind of jumping about on the lattice. And we can also think of, let's say, a missing lattice site that comes with necessarily an unpaired spin half. So so now we can we have here at this white ball, we have a missing, let's say, if this is an electron, a missing charge, and an excess of spin half here. So we can see that now that the electron broke down into its charge and spin degrees of freedom. It's sometimes called spin charge separation. So it kind of shows about really neatly in such models. I won't say a lot more about this. What I will say is that if we now go back to just monomers, no spins, then the different phases treat the monomers really differently. So in the states that are ordered, let's say the columnar and staggered phases, then you can see that, let's say in the staggered phase here, there is a line between the two monomers where you have flippable plaquettes, which the staggered phase doesn't like. It gives a penalty for flippable plaquettes. So the larger the distance between monomers, the larger the energy of this configuration be, and it will actually be proportional to the distance. So this is behavior is called the confining behavior, where if you now look at fluctuations about the ground state and you ask, okay, how far away will you find the monomers, then they will be fairly close because there is an energy penalty associated with them being far away. In the RK point, it's a little bit different. You can calculate the monomer-monomer correlations, again, using Pfaffian techniques or modified. It's a little bit more subtle for the monomer, but you can do it. And for the square lattice, you get...
What do you mean in the RK point? The RK point doesn't have any monomers. So what do you mean by the RK point now?
So what you can do...
It's like an excited state of the RK point.
So you put two monomers and
yeah, you put by hand, let's say, two monomers, and consider how many dimer configurations you have.
But so in this model, you add you before you had a model that had some terms for the monomers.
Yes.
So this model you consider go back
something like this.
But then, how do you tune this T and VH? T.
So the T is the same as before. The VH you can it's just kind of I think it's taking to be 0, if I remember correctly.
So T is equal to the T of the RK.
Yes, it's the same. It's the same kinetic term of the bonds hopping about.
Okay, so that's what you call RK point now.
Yes. So it's kind of it's a larger Hilbert space.
Okay.
Barak.
Yes.
In the topologically non-trivial state, state when you make monomer, it breaks the topological order. Is it somehow related to the to the fact that in those states you have confined excitation?
Again?
Okay, can you ask again?
So in the staggered state, we know that it is topologically non-trivial, and when you make monomers, when you move monomers away from each other, they cost a lot of energy. While in the columnar state, in the columnar state, it's trivial.
What do you mean trivial?
There's no topological order in the columnar state.
The columnar state, in both the columnar and staggered states, you have this confinement where
they're both confined. Yeah.
They both
they're
are
both-
confined?
Yes, both the columnar and the staggered are confined.
Oh,
What I want to say is that on the triangular lattice in the Z2 RVP, and exactly for the square lattice, exactly at the RK point, you don't have this behavior.
okay. Okay. Yeah, thanks.
You don't have the behavior of the
Thank
confinement.
you.
You don't have the behavior of the confinement.
Yes, you don't have the behavior of the confinement. And that can be viewed. Let's say you view the monomer correlation. So if you did have confinement, you would expect to have exponentially decaying correlations.
Yeah.
But that's not the case for the RK point. So for the square lattice, it's not exponentially decaying, but it goes something like this. And that's the asymptotic behavior. And on the triangular lattice, it actually goes to a constant, meaning that you can find the monomers arbitrarily far away from each other. So this behavior, I think they're both called deconfinement, but in the triangular lattice, it's more deconfined than on the square lattice in some sense.
Okay.
Okay, so I want to talk about another type of excitation in the RVB. So we discussed a little bit the monomers and how they behave. Well, before I said the RK point of the triangular lattice, but we can also kind of extend it slightly, use numerical techniques to kind of probe the monomers. Another type of excitation is what's known as visons, and these excitations, they live on the dual lattice. So if we are on triangular lattice here, they live, let's say, in the middle of a triangle, in the middle of the plaquette. And the way they can be thought of is they can be thought of having this line going out of them, and this line needs to end at either the edge of the system or another vison. And the ground state will be an equal superposition in topological sector of the dimers with plus minus signs that correspond to the number of dimers that cross this line. Okay, so it can be shown at the RK point. This is exact. It can be shown, and for other points, you can use this as a variational wave function for an excitation.
Oh, what's the definition of this vison again?
So if you just look at a quasi-particle excitation that doesn't introduce monomers, this is what you will find in the Z2 RVB.
What is this? I'm trying to see what is a sharp definition of this.
So at the RK point, you'll find this form of the wave function, where you have like the quasi-particle lives on the dual lattice, and it has a line extending out of it. And in the wave function, you have this alternating sign depending on how many dimers cross this line.
No, but it has to be a function of the dimer configuration. How is it depending on the dimers?
What do you mean?
If I look at it, how do I know to put the vison there and not somewhere else in the lattice?
Well,
what?
This is the excited state with vison living on this site.
What is the vison? Yeah.
Is there like a local operator that will tell me where's the vison sitting?
Yes. Okay. Good question. So if you were to take a dimer, a monomer, and kind of move it, loop it about a vison, you'll get a sign reversal of the wave function.
What does it mean? What does it mean to take a monomer around the Vison?
So you can think of, let's say we have a dimer. We have a dimer.
Break the dimer.
You break the dimer, and then you kind of start moving the monomer about till it comes around, and you combine them back together to a dimer.
I see.
So this is in the transition graph. You want to define the excitation according to the transition graph of the configuration with what? Some other configuration. And you want to give a complex weight to the transition graph.
I don't quite compare the configuration themselves, because I need the whole superposition of dimer graphs with the correct signs here to get the Vison. Just looking at what dimer configuration won't give me this sign reversal.
Right. So it's the relative phase of two dimers that are shifted with respect to each other to give you your loop, and you weight the loop with a minus sign instead of just pluses, which was the original RVB state.
Oh yeah, that's another way to view it. Yes.
Okay.
Okay.
So this is kind of a local operator that probes if you have a Vison at some site. And just to relate back to the loop picture, we have we saw that the monomer correspond to open loops, or not loop, open strings in the transition graph. So it's very similar to the toric code to the, I think, E excitation. And the Visons are similar to the M excitations, that they live on the plaquettes, and then you get a minus sign when you go about them. So the Z2 RVB phase can actually be viewed in some sense as the toric code ground state.
Where in all this discussion did you assume it was an RVB state?
So that's in this discussion, I discussed the Vison at the RK point of the triangular lattice or non-bipartite lattice, which is in the Z2 RVB phase. If you want not to look at the RK point, people have looked at this numerically again and saw similar behavior.
The RK point on the triangular lattice, which is this RVB.
Yes.
Asa, how did you say you think about this Vison? I didn't follow you.
It's in the definition of the weights of a loop. Mm-hmm. So you have to have non-orthogonal dimers, and then if you look at the overlap between two loops, you give a weight which is not just the length of the loop we saw before, but the length of the loop times I in the exponent, right? I times pi times number of, that times the position of essentially the flux in that loop. So here he says he has a pi flux in this black and red loop. So it's something in the loop weights that becomes, giving you complex phases.
Yes.
It's not in a single dimer configuration, but of course, if you write the superposition of dimers, you're also giving the weights of loops, right? Because the dimers are non-orthogonal. So having minus signs in the sums over dimers will give you that effect.
Mm-hmm. But here in this discussion, we are assuming back that the dimers are orthogonal, right?
Yes. Here in this discussion, the dimers are orthogonal.
Yeah, but then you cannot define, then there's zero weight to any overlap, so you'll never see the minus sign of the Visons.
Why not?
It comes in the off-diagonal terms. It comes in the, the green and the black are not the same dimer configuration, right?
Mm-hmm, right.
And you need to define a closed loop.
I can still in the superposition put minus signs relative to the ground state of the system.
Right, but if all these D's are orthogonal, then what is the meaning of the minus signs? I mean, right, you can always take orthogonal states and multiply them by minus signs.
Yeah, that's right.
Yes, but you can ask. You can also ask. Let's say here in this operator, I specifically took a minus sign here. And this minus sign is important, right?
But Barak, it's a gauge invariant. I mean, it's a gauge choice, right? I could choose to multiply states by minus sign. Yeah, and then the question is whether that would change something in the Hamiltonian or not.
So again, if I let's say just look at this term,
yeah,
then it treats differently these two states.
No, that's for sure. Yeah.
Yeah. So the despite the fact that we started with kind of a phase ambiguity or sign ambiguity of each dimer configuration, when we wrote down this specific operator, we somehow constrained this. We constrained this phase.
Yeah, Asa, I think that the point is that the Hamiltonian can have off-diagonal terms between those Ds. So,
I know, but he's talking about the state, not the Hamiltonian.
Yeah, but right. Yeah.
And his state requires some overlap of different dimer states.
Yeah. So
to define the Vison. Otherwise.
Yes. So to define the Vison using this kind of loop about it, as I said, I move monomers about it, and the movement of monomers is with this specific phase. So I kind of choose a phase in some sense.
Yeah. Mm-hmm. That would fix the phase.
Okay, that will mix the. Okay.
Okay. So these are the two excitations of the quasi-particle excitation of the Z2 RVP. And now yes.
So this is true only at RK point or also way, because you know, positive superposition is only the ground state at RK point.
So the positive superposition is the ground state of the RK point. This Vison wave function I wrote down is the excited state at the RK point. Away from the RK point, the ground state will be some superposition of diagrams, and the excited Vison excitation of a Vison will also be some superposition, but it won't be necessarily this. I mean, the sign structure of the wave function will probably be similar, but the weights will be different.
But you still can define this Vison.
Yes, using let's say this kind of local operator that measures if you have a Vison at some site. Okay.
Yeah.
Okay. So I want to discuss one last neat feature of the RK models, which will also appear. I'll also discuss it soon in the Majorana dimer case, in which is we can get exactly solvable models, and by exactly solvable I mean finding the ground state and all the excited states, not just let's say as in the RK point where we found only the ground state. One such model is just the RK model at the Kagome lattice, I think I'll skip most of the next slide. The important thing here is that on the Kagome lattice, you can ignore all the arrows and such. On the Kagome lattice, all the plaquettes, if you think of a basic move, I think I didn't put a picture of how you flip a dimer on the Kagome lattice, but essentially if you ask if is a flip move available on some dimer configuration, then the answer is always yes. All plaquettes, and here in the plaquette I mean the hexagon plaquette. You obviously can't flip a triangle. You can't flip, let's say, one occupied dimer to two touching dimers. That's forbidden. But the move that involves the polygon with even sides, the hexagon here, it is always okay to flip it. Okay, and so you can think of, do I want to say it? So you can think, so any loop is valid, and the dimer correlations vanish beyond one lattice constant. Another thing before I continue to another lattice is the model, as I said, it can be exactly solvable. It can be mapped exactly to actually the Tori code on an hexagonal lattice.
This is in the Kagome, you're saying?
On the Kagome, yes. On the Kagome, and also on the Fisher lattice or star lattice, it's called. Mm-hmm. This is the same as the Kagome, only the triangles don't touch each other. They have this bond connecting them. And here I did put some pictures of allowed moves. And so this is another lattice that in the next work I'll talk about in the Majorana case the authors consider. And it also has this property that all transition loops, all the loops on the dual lattice gives you a valid transition loop, and it can also be mapped. The Hamiltonian can be mapped to the Tori codes on the hexagonal lattice.
Okay, so
okay.
To say that the Kagome you're saying is exactly solvable, and it can be mapped to the Tori code. On the Kagome dimer can be mapped to the Tori code.
Yes, the Tori code on the hexagonal lattice.
Can you just say again how you do that? Sorry, I missed that.
So,
is it important to the next topic or not?
It's not. I didn't plan to say much about it. If you want, I can come back to that later.
Yeah. Okay. Mm-hmm.
Just I don't want to take too much time.
Yeah,
because,
okay. Continue. Mm-hmm.
Yeah. Okay. So now we're ready for the next part, which is the Majorana-quantum dimer model. So I'll kind of go briefly through what I'm going to talk about. I'm going to talk about how we attach Majoranas to the constructions of the dimer models I discussed so far. I'll give some parity considerations of the model. It will be quite interesting, I think. And we'll see that this will give two models using these Majoranas glued to a dimer model that I'll claim that they realize the Ising cross P minus IP phase that has a non-abelian Ising order and gapped edges. So it has no edge modes. Okay, so let's dive right into it. So Majoranas, this is just a brief reminder. They are Hermitian. They obey the Clifford algebra. Two Majoranas are equal fermion. This is the equations, and you can think of the occupation of this fermion as given by the parity of the occupation of a fermion is given by this operator combination. And I can summarize all of this in the following equation. Okay. So if we now put Majoranas on some lattice, then we need to say, so if we just want to pair up two, let's say we have Majoranas on the vertices, and we want to pair them up, we have two ways of doing that. Either I gamma 1 gamma 2 equal 1, or I gamma 2 gamma 1 equal 1. So another way of thinking about this is that we say that these two Majoranas form a fermionic degree of freedom, but we need to choose which Majorana is the real part of the fermion and which is the imaginary part. And this choice can be kind of pictorially shown using an arrow or giving an orientation to the dimer, the specific dimer we are looking at. And so if we have an arrow from gamma 1 to gamma 2, we say that I gamma 1 gamma 2 equals 1. This is our choice of how we form the fermionic degree of freedom that we don't occupy in this case. Okay?
Mm-hmm.
Okay, so now we can think of a superposition of such pairings of Majoranas. So it kind of looks like an RVB. Currently, I didn't say anything about the orthogonality of this, but again, just a superposition of these. And a thing we need to be careful of that the sum in this sum of superposition of Majorana states, we want all the here I said dimer configuration, all the Majorana configurations, we want them to have the same total fermion parity, because it's kind of unnatural to stumble across a state with undefined total fermion parity. Okay. So in the paper, they actually give a really cute proof that if you want to kind of compare the total fermion parity of two dimer configurations, let's say in these two pictures, an easy way to do that is to look at their transition graph. And here we also look at the orientation of the dimers or the links, and these two states, if for them to have the same fermion parity, what we want is them to have that every loop obey the clockwise odd rule. Okay, so if we go along the loop and we count the number of links that point against the way we're looking, we want this to be odd. And this is essentially just the Castellian orientation. So we know we can guarantee this on let's say on a planar graph. On a planar graph, we can before writing down any Majorana state on the RVB, we can choose beforehand how we'd like to pair up the Majoranas if they were dimerized, and this will give us a consistent choice of the arrows. So we're guaranteed to have the same fermion parity in all the Majorana configurations.
Okay, can you say again, each dot, each red point represents a
Majorana
or a fermion?
A Majorana fermion. Each point is a Majorana fermion. A pair of them is well, it's a fermion, and if we have this kind of line, an arrow pointing from these two, it means that, and here we have gamma 1, gamma 2. Let's go back.
I see. So that tells you which gamma it is. I see.
Yes.
Yeah. Mhm.
Can you explain again why gamma 1, gamma 2, and gamma 2, gamma 1 give you a different fermion parity?
So because gamma 1 and gamma 2 anti-commute, you know necessarily that I gamma 1 gamma 2 equals to minus I gamma 2 gamma 1. Now you know that if you look at the fermion way of looking at this operator, this being equal to plus minus 1 just tells you if you occupy or don't you don't occupy the fermionic state that's composed of these two, right? So choosing which one here is which is first in this operator can be thought of as just choosing which one of them is the real part of the fermionic degree of freedom, which is the imaginary part, right? If we go back to this equation here, so the gamma 1 is the real part of C and the gamma 2 is the imaginary part. Okay?
Yeah, okay.
Okay, so we again met our friend Castellane. This time not using the Pfaffian to write down the classical partition function, but actually when we wanted to guarantee to have a consistent fermion parity. Here are two Castellane orientations for the triangular lattice and the Fisher lattice. The blue bonds will be the reference dimers that the continuation of the results I'll discuss will relate to.
So in these pictures, the blue links are the one you put I gamma 1, gamma 2, right?
So if no matter which link you choose, let's say we choose this one and this one, then we choose them to be paired that this is the gamma 1 and this is the gamma 2.
Yeah.
And if we were to choose this and this, then the arrow tells us how to. Yeah. That's the arrow. It gives us a consistent way of choosing which is the gamma 1, gamma 2. The blue links are just kind of a reference dimer configuration or a reference Majorana configuration.
So these are
useful when you.
The blue links are with the occupied fermions in this, right?
This reference, yes. Yes. Okay. So another thing before I kind of discuss the Hamiltonian, the Hilbert space in the Hamiltonian, is we can, as I said, the Castellane orientation, we're guaranteed to have one on a planar graph, and you can ask, okay, what happens if we're on a torus, because we like tori. So it actually gives you a really neat feature that because you have non-contractible loops, that if you compare state in the 0, 0. So a non-contractible loop is it just count it's again the topological index that relates to this kind of loop, and we have also this kind of loop. So it's Z2 times the Z2 topological index on the torus. And if you now use this, you modify the clockwise odd rule to these non-contractible loops, you'll find that the parity of the state here will be opposite to these. I mean, you need to also fix the Castellan orientation, and then you'll find that these three sectors necessarily have a opposite fermionic parity with when you compare it to this topological sector.
Say again, what's the difference in terms of the state between these three sectors? I'm not sure I understood, sir.
So if we take the Castellan orientation, either one of these, let's say, on the torus, and in the and we can look at now the different topological sectors on the torus. So these different topological sectors have Z2 times Z2 index that corresponds either to the parity of dimers you cross in this loop, or the parity of the dimers you cross in this loop. And now you compare the parity of states here, and again the parity now is determined by the Castellan orientation. You can't now we don't allow now exchanging the roles of gamma 1 and gamma 2, let's say, on this bond. The choice of which one is gamma 1 and gamma 2 is determined by the Castellan orientation now. So the Castellan orientation, the Castellan orientation guarantees that if we look at some specific sectors, they all have the same parity, but different sectors will have different parity because of these non-contractible loops. I'm not going to show this claim, but just kind of say it. Is that clear?
Oh, I don't know, but we can skip this. I don't understand what do you call a sector?
So the sector is it's what it was in last time. So if we go all the way back, all the way back to the topological invariance of the dimer model. So we just look at a non-contractible loop, and we look at the parity of the numbers of dimers that cross this cut. Okay. Okay. So let's go back. Okay. So now I finished discussing the parity of the Majorana dimer models so now as the Hilbert space of the model, we'll consider now, instead of just Majoranas, we consider Majoranas that are attached to a dimer model. So we have here the dimer model Hilbert space. Again, the dimer configurations are an orthogonal basis of the dimer Hilbert space, and we have the fermionic state, or the Majorana state here, that just according to the dimer configuration that we chose, and the Castellan orientation that what we chose even before that, we get a specific Majorana state. So this is just the tensor product of the two. Okay, so choosing the dimer configurations fixes the Majorana part of the wave function. And we take
orientation.
Yeah.
You fix the orientation, and then
yes. The orientation is fixed from the start, and now we look at the dimer configuration.
So why do you say the Hilbert space is a tensor product? D, and f of d is defined by d. Well,
yeah. I mean,
there's no freedom. I mean, there's no different. It's not that what d fixes the Majorana state, right?
Yes. So in our case, yes. D fixes the Majorana state.
Okay.
Okay. Now that we wrote down the Hilbert space, we can look at the Rochsal-Kivelson model using with this Majorana attachment, and we have the potential term that just kind of counts how many flippable plaquettes you have. I don't write it down. And for the kinetic term that flips the dimers, we have because we have the choice of phase, then we can play with the phase relation of this. Here we have this kind of I pi over 4. I'll soon explain how this is chosen. So we have a flip move, and on the Majorana part of the wave function, we need to act with some braiding that will exchange the two pairings of the Majoranas. This braiding operator is written here. So it's I plus S12 gamma 1 gamma 2. S12 just tells you the 1 2 is depicted in the picture here, which one is 1 and which one is 2 in the flip move, and the S12 just tells you the directionality of the bond between the 1 and the 2. Notice that the third term here and the fourth term here, they look the same. They flip. It seems like they flip the same bond, but actually they differ because the Castellano orientation breaks down the translation invariance and enlarges the unit cell of the model by 1. So it depends on if the link that connects if let's say the one link here has let's say an outgoing arrow. Where's that? An outgoing arrow like here, an outgoing arrow, or an ingoing arrow, or if you compare it to the reference dimer configuration, whether the link combining them is blue or not. Okay, so in the paper they say that this choice of phases is the preferred choice of phases with this strange I pi over 4. The reason this phase is like so is because it gives you the magical relation that the matrix element, if you compare two dimer configurations with the with the corresponding fermionic part. So if you compare them, the matrix element of this operator, it will be the same as that of the non-Majorana RK Hamiltonian if they are connected by a contractible transition loop. Okay, so two states you can write down the transition graph for them and look at the loops that relate them, and for a contractible transition loop, this will just be the same as in the non-Majorana RK Hamiltonian, and that's
what is the P supposed to mean?
It's the P is the plaquette. So it's a dimer flip of the P plaquette, let's say. It's the same P here.
Saying this choice of BP, basically something that looks like the classical.
Not classical, just the non-Majorana RK Hamiltonian. So if you just kind of look at only the contractible point, so we know that for our open boundary conditions, let's say we're on an open disk, we don't have any contractible loops. All states are related by all the transition graphs have uphold these conditions, and the Hamiltonian will just have the same matrix elements as the Majorana RK Hamiltonian will just have the same matrix elements as the non-Majorana RK Hamiltonian. So we know that the spectrum is the same. The spectrum of the Majorana dimer model in this triangular lattice is the same as the triangular RK Hamiltonian. So the phase diagram is also the same. And we know that in the non-Majorana case we have no gapless edge modes. So in the Majorana dimer model we also have no gapless edge modes. So this is a pretty neat result. You can also ask what happens on the torus. So on the torus it's more complicated because the RK point is no longer you can no longer solve it using Pfaffian techniques, or it's more complicated. I think there's a recent paper that shows how it's done, but it came about after this paper was published. So what in the paper they do is they just look at the 4x4 torus and use exact diagonalization, an exact calculation to find the ground state, and what they found surprisingly is that
again, the ground state of Barak is the ground state of what again?
The ground state of the triangular Majorana RK model at different topological sectors, which are depicted using the red line here, or the absence of a red line here.
But it's not the same as looking at the original.
No, because the condition for the original was only for contractible transition loops, and in this case you have non-contractible loops.
I see.
So the presence of these non-contractible loops and the Majorana part of the wave function gives you a difference between these three sectors that have odd fermion parity, and this sector that has even fermion parity, and the one with the even is actually has a higher energy, about numerically they found it to be 0.14 T. And if you kind of calculate, they also found that there is a Bison somewhere on the presence of a Bison. You just kind of go about all the plaquettes and calculate for a Bison. You find there is a Bison here, a single Bison. So this is different than the non-Majorana case. In the non-Majorana case, you had 4-fold degeneracy on the torus. Here you have 3-fold degeneracy. So we can also, what they also consider is also the model on the exactly solvable Fisher lattice, or it was exactly solvable using the non-Majorana construction. For the Majorana, it stays exactly solvable, which is nice. So they also consider this to study the phase, and yeah, with the appropriate, I won't go through all of this slide. The appropriate phase choices, and there is they say how you want to write down consistently the phase. Essentially, what you want from the phase choices is that the plaquette moves will commute. Okay, this is what you want from the flipping of plaquettes on the Fisher lattice or triangular lattice. This is the condition you want. This fixes the relative phase of the plaquette moves, and the Hamiltonian now becomes just a sum of these plaquette moves. You can ask what happened to the V term, right? You had also the V plus a number of flippable plaquettes, right? But if you remember on the Fisher lattice, all plaquettes are flippable, so the number of flippable plaquettes is constant, so this term is just a constant you can ignore. So the RK Hamiltonian is just the sum of the kinetic terms, and the kinetic terms they commute on this model, on the Fisher lattice. So it's a sum of commuting terms and the sum of local commuting terms. They also, in the paper, they kind of show that this you can also worry that this phase choice might give you non-local terms, but in the paper they also show that it gives you a local commuting Hamiltonian. So since the Fisher lattice is a Hamiltonian is a Hamiltonian of local commuting terms, then the Hamiltonian is fully gapped, even with boundaries. Okay.
Barak, how much more do you have? I'm thinking
So then
continue when we finish next time, because A, I'm running out of time. B, I'm running out of steam.
yeah. The rest part I have is discussing a little bit the topological structure of the model, entanglement entropy, and then modular matrix. So it's I need like I think 15 more minutes or 10 more minutes, something like that.
Okay.
1, 2, 3, 4, 5, 6.
Okay.
6 slides.
Continue.
Okay. So I'll try and summarize so far.
Yeah. So go back a bit, and we're looking at this Fisher lattice.
Yes. So on the Fisher lattice, we have the RK Hamiltonian becomes an exactly solvable Hamiltonian that can be viewed as sum of commuting terms. So it's an unfrustrated model with fully gapped states, even with boundaries. You can also show that the ground state degeneracy persists. The structure of the ground state degeneracy persists also on the Fisher lattice, the same as on the triangular lattice. So these three sectors form the ground state subspace, and this sector is in an excited state. So on the torus, it's threefold degenerate, and you can also extend this to higher genuses. 1 second. Forgot I'm not in a presentation mode. So now you can ask yourself, okay, what type of topological phase is this? We know that this phenomena of having a degeneracy that's associated with the genus of the surface that the system is put on is related to what type of topological phase we have. So it already kind of seems like an Ising topological order. And for those who don't know, one of the hallmarks of the Ising topological order is that it has threefold degeneracy on the torus. Another really prominent way of characterizing topological phase is using the entanglement entropy. So if we now look at the torus and we cut it into two subsystems, so here we need 2 cuts to divide it, because we still remain with a non-contractible loop on each cut. So the entanglement entropy on this system, because it's gap, we expect it to have this area law, some constant time L, the length of the cuts. And we also have, so the alpha coefficient is non-universal, but the entanglement entropy is also have this shift by a constant gamma that is universal. It shares the same gamma with all system with the same phase. And this is something that for me it was new. This gamma will actually depend on the state of the system. Usually people don't mention this because it doesn't depend. But in the case that the region that you restrict yourself to, this A region is topologically non-trivial, then this gamma will depend on the state that you started with. And it has been worked out what this gamma is and how it relates to the anion structure of or the topological structure of the state. So if you have the state that's characterized by this A, where A is you can think of creating an anion anti-anion pair and then moving them across this non-contractible loop and then calculating the entanglement entropy. So this gives you this gamma A. So these states are also called they're also called minimally entangled states, because if you look at these states and perturb them locally, you will necessarily get a higher entanglement entropy. So they have locally minimally entangled state, minimally entanglement. The states that kind of minimize this locally, and in
What
this
is
case they are
D, capital D, and small d?
Yeah, so capital D is the for those who don't know this, don't worry too much. It doesn't matter for the rest of the lecture. Capital D is the total quantum dimension of the anions in the system, and the small d is the quantum dimensions of the anions. So for fermions, small d is 2. For Majorana, small d is square root of 2, let's say. And then the capital D is the sum of all the different anions you have in the system. Okay?
Okay.
So in this system, we have threefold degeneracy, and we can look at the three minimally entangled states. These will be these three, and then they're labeled here 1, 2, 3, and the state 1, 0 here. This just relates to which topological sector, grounds to which topological sector you're looking at, and these phases are kind of found using just minimizing this on the rather small 2x2 Fisher lattice model. So just kind of brute force, you can find these three, and you can find the entanglement entropy for them. And this entanglement entropy actually looks consistent with the Ising phase, meaning that the probably the quasi-particle, the anionic quasi-particle in the system are identical to those in the Ising phase. And because it has gapped boundaries, we can think of the following candidate. Just look at the Ising of type N, and we need something to gap the boundaries, which will be something like this, px minus ipy. So
what is n? Ah, I see. Okay, yeah. Mm-hmm.
Just the power. So the Ising N model has this central charge, and the p minus ip has
chiral.
Yes, chiral center charge. Sorry, this chiral center charge, and the p minus ip. The minus is important. Has the opposite chiral center charge. Mm-hmm. So in this kind of our guess, the total chiral central charge is 0, which is actually needed if we want gapped boundaries. If it was different than zeros, then that would be that would necessarily imply that we have gapless edge states. This is just a table of the Ising of the anions in the Ising N model. N is just there are different types of Ising models, with n being some odd integer, defined mod 8 here. So we have this kind of candidate for the ground state, and we can ask what the n is. And to do that, what they do in the paper, it's a really neat trick, and they look at the modular transformation, or the S and T matrices, which I'll soon explain, and relate that to the behavior of the Ising model. So so what are the S and T matrices? These are just two symmetries of the model on a torus. So on the torus, you can think of if you identify this edge and this edge and this and this edge, you can also kind of rotate by 90 degrees, and it will be the same model, right? Just glue the same way. It looks kind of weird on the torus. It looks like this. So now the red arrow going down here is rotated to this one. So the rotation is done before you glue the edges. So you get something like this. Another symmetry, the T symmetry, is pictorially shown here. We know that on this picture of the torus, this edge is the same as this edge. So instead of gluing this to this, we can glue this to this. And we know that this edge is the same as this edge, so we can glue these two. So it's the same torus. So it should be a symmetry of the Hamiltonian. And pictorially, it can be shown as taking the torus, cutting it, twisting the region of the cut, and then gluing it back together. So this is the S and this is the T. And these are known to span what's called the modular group. It's kind of mathematical structure that people have been interested in. What's important for me here is that the S and T matrices are believed to uniquely determine the topological order in bosonic systems. So if we're able to calculate the S and T in our system, which isn't bosonic, but still, if we're able to calculate the S and T here, then we might be able to determine what the n of the Ising n is. So in the paper, so here's what we expect. We expect the S matrix to act on the Ising and the P minus IP part, and also the T. And these are just the, if you look at the book that explain what are the S and T for these two models, these are the matrices. So this is a 1x1 matrix, and this is a 3x3 matrix. So this is what you get. These are kind of known results. And if we want to do to kind of relate this to the Fisher lattice and see what the n is, then we can. So they have a clever trick here that the S times T, the inverse T, can be viewed as a 2π/3 rotation. So which is a symmetry of the Fisher lattice, and you can see how the symmetry acts on these minimally entangled states, the basis of minimally entangled states. And from this you can extract the n actually.
Rotation with the with open boundary conditions or with periodic?
No, on the torus. Everything here is on the torus, right? The modular transformation.
How do you find this rotation?
So they just do brute force on again. It's everything is on the 2x2 size Fisher lattice. So it's really small. In the paper, they say that they try to do this on the 4x4 triangular lattice, but they think they have some kind of finite size effect that gives them weird results. They don't say exactly what they get in the numbers there, but on the Fisher lattice 2x2, they get this R kind of just by brute force. You know what the symmetry is. You can relate two wave functions using this symmetry, and you find this matrix. And if you kind of compare it to these textbook matrices for the Ising n and the p minus IPn to the n, you get that this is consistent with n equals 1. Okay, so they have some other neat ideas in the paper that
Barak?
yes.
Probably I missed this point. So is the time reversal symmetry broken initially, or it breaks spontaneously?
I think it's broken. It's broken, but initially it's not.
I think
the model doesn't have symmetry.
Yeah, I think the choice of Castellano orientation breaks it. Okay, so last slide. I won't say much about it. They have some other ideas. They look at more than one Majorana on each site, which gives you some other interesting phases. You can relate these models to the eightfold way of Z2 fermion symmetry protected topological states. I won't say much about it because I already talked a lot. So this is a quick summary. Last time I showed what are dimer models and RVB states. I talked about what is the RK Hamiltonian and what is the RK phase diagram, with the distinction of bipartite and non-bipartite. I also talked quite a lot about the RK point in relation to classical dimer model and the transition graph and exactly, and we also showed the transition graph that plays the role in these dimer models and some exactly solvable cases on the Kagome and Fisher lattice specifically. I kind of showed you how you can see fractionalization phenomena in these models. And then the last part, we discussed the Majorana-quantum dimer models as an extension of these, in which the parity played a crucial role, and I showed two models for the Ising times p minus IP phase, and tried to convince them that this is indeed the characterization of the phase. That's that. Thanks for listening. Any questions?
Yeah, can you quickly again say how this Fisher lattice becomes exactly solvable?
So at the non-Majorana case?
No, on the in this case, in the Majorana case, unless it's very complicated. So another time.
So the basic idea, where is it? The basic idea is the same of how to extend the triangular or the Fisher lattice. In both cases, you, as Asa said, you have in the dimer model, you have kind of a sign choice. In the fermionic case, you can also think of it as just a phase choice. It's you need to fix somehow.
Okay.
So you can either fix it in the wave functions, or as I said in the non-Majorana case, you can look at the operators and demand some kind of phase consistency between the different operators, and what you want to, the way you want to fix the phase. So for the triangular lattice, there is this I pi over 4, e to the I pi over 4 phase, and such. So in general, for the Fisher or any other lattice, you want the different plaquette moves to commute.
Mm-hmm.
Okay.
Okay.
So,
the,
Barak, so I should think about it as fermions, or Majoranas are, combined into fermions. These are fermions living on bonds, hopping around in the presence of some gauge field. That is the Castellane convention. Is that the way to think about it?
I think, yeah, it can be thought of like that. Yes, actually, in the last part of what I didn't really say, the way in the paper they kind of present it was, oops.
Yeah, so it cannot just be hopping because this is a kind of strongly interacting model. Otherwise,
Yes.
it's Ising phase.
Where are the
so
interactions? I don't see interactions. I only
Because
see.
it's because this hopping is not, you know, these moves are not one hop of one fermion. They could be hopping around multiple fermions at the same time. So it's not a quadratic operator.
Ah, okay.
So a neat way in the paper they say you can think about these models is I discussed just the n equal 1, so you can think here of n equals 1. You can think of starting with a Z2 fermion SPT where you have kind of just a bilayer, let's say, of P minus IP and P plus IP, and you gauge the P plus IP. You gauge the fermion parity and get an Ising phase, and that's how you get the model. So the model is obtained from the fermion symmetry protected phase, and you can also, in the paper, I didn't really read that part, but they say you can also kind of go back and ungauge it and get the model for the fermion SPT. So that's just a different way of thinking of this model. Just the P minus IP and P plus IP, that the P plus IP is gauged.
Beyond those fancy words, you're somehow saying that this
yes
can be chosen such that they all commute, basically, right?
Back to the commutation of the
IPT.
Yeah. Back
again, what?
Lattice, you're saying these can be chosen to be
receipt.
I can't hear both of you simultaneously. What do you...
יכול להיות.
אני חושב שיוסי בשיחה אחרת.
סליחה, כן. מדבר עם אשתי לפעמים גם.
So what did you ask, Nathaniel?
So those B's can be chosen to all commute, you're saying, in the Fisher lattice. That's the point.
Yes, yes. And they can choose to all commute in the Fisher lattice. And also you don't have the potential term because all plaquettes are flippable. Right?
What did you say again?
On the Fisher lattice, all plaquettes are flippable, right? We had this.
Right.
Yeah.
Yes.
So we don't have the V term is absent. We don't have it here, which only leaves you with these commuting terms. So in the triangular lattice or whatever, the V term is non-vanishing. It plays an important role. On the Fisher lattice, it's just constant.
So why did they have to? I'm confused. Why did they have to study this model numerically if it's all the sum of commuting terms?
So that part, I think it was a simplification. If you want to find, I mean, I at least don't know much about this, but the minimally entangled state, you want to find these. I think it can be really hard to do this. I mean, from what I understood, they did it kind of brute force on the 2x2 lattice, Fisher lattice, and on larger lattice sizes, doing this brute force is harder.
I see. But the model
their justification for this is that on the Fisher lattice, the correlation lengths of dimers vanish after one lattice site. So they said something like it's enough to look at the 2x2 case.
But finding a ground state, I mean, the model is exactly solvable. So finding some ground state should be easy. But maybe finding these specific ones is the problem.
yeah, I mean, just kind of saying, okay, I want the state with all let's say, all the B's equals 1 is okay, but writing that state down and calculating expectation values for that state can be a little bit harder, I think.
I see.
Any other questions?
So this, I see. So you had some expressions in terms of some sigma times something else.
I didn't write that down, but in the paper they do have it. Let's see if I can.
You had it. You had
if you want, I can show it. I had it.
Yeah, you had it.
No, I didn't really write it down. It was only. It's really complicated. I mean, the B, you can think of it as acting on the plaquette as flipping. It's like flipping all the dimers on the dual lattice. So here, the dual lattice is an hexagonal lattice, right? So it's like similar to the Kagome. I have a picture here. So if you look at the green lines here, they form, it's the dual lattice of the Kagome lattice. It's hexagons. So it's something similar. In the Fisher lattice is the same. And these, where was it? These sigma x's that flip, they flip actually the signs on this dual lattice. The other part here, BP, is the fermionic part. This really isn't, doesn't give you explicitly the expression, but it is a formula they derive. In the paper, they have this kind of lengthy expression for the fermionic part of the plaquette move. Okay, so the BP is just a phase, and the phase is determined in some, they have some consistent way with the commutation of the different plaquette moves.
Okay. Okay, any other questions?
תודה רבה.
Okay, אז ברק, תודה רבה. איליה,
Thank you for listening.
Yeah, keep this recording. Maybe we'll give a link to it somewhere. You guys think?
That would be nice.
Yeah.
Okay.
Okay. Okay.
Okay. Yeah.
Okay. So next time we meet after the Pesach holidays.
Yeah. Okay. After Pesach. Okay.
Yeah.
Okay, guys. So I guess tomorrow we'll have an archive meeting. Yeah.
Oh yeah, we do.
Okay. So see you tomorrow then.
Yeah, see you guys.
Bye. Thanks.
Bye.
Bye-bye.